Hello everyone, welcome to the spring semester 2026 in organic chemistry. The last time we just finished lectures on alkenes through lecture 32 to 35 on alkenes, which included their properties, their reactions, and mechanisms, and so on. So in this series of videos, as a chapter end, I will be solving problems that are related to alkenes. So I really encourage you to understand and review the lecture in lectures 32 to 35 and follow up with the problems and the tutorial section. Thank you. Okay, let's begin our problem solving session by starting from an easy question where it's asking you what is the degree of unsaturation. That means how many rings or double bonds are possible with this molecular formula. So as you know, alkenes are unsaturated. That is what you are trying to figure out, how many unsaturation or how many double bonds. Or rings. Rings also make the molecule unsaturated, meaning that at least you need to lose two hydrogens to make a ring. That's why it's also called rings plus double bond. Let me put the formula first. The formula for rings plus double bond is 2 times the number of carbons in the molecule plus 2. If you have a nitrogen, number of nitrogens, and then minus the number of hydrogens or halogens. That means bromine, chlorine, fluorine, iodine, etc. Now you divide that by 2. That will give you the degree of unsaturation, the number of rings and double bonds that are possible. So let's solve C3H4. For C3H4, the number of carbons is 3. So I will calculate 2 times 3 plus 2 is in the formula. And we don't have any nitrogen, so minus the number of hydrogens, which is 4, over 2. That is 2 times 3, 6, 8. 8 minus 4 over 2 is 2. So this formula, C3H4, can have 2 degrees of unsaturation. So I can propose, for example, a structure for this, such as this cyclopropene alkene. It has 1 ring and 1 double bond. That's 2. It could be all rings, it could be all double bonds. Let's do C10H16O2. 2 times 10, number of carbons, plus 2, minus 16, the number of hydrogens, over 2. That would give you 20. 22 minus 16 is 6 over 2. It should be 3 degrees of unsaturation. So this molecule can have 3 alkene groups, meaning 3 double bonds, or 2 double bonds and 1 ring, or a combination. So that is the degree of ring plus double bond. For this formula right here, you have 2 times 4 carbon plus 2 and nitrogen plus 1, you have 1 nitrogen, minus the number of hydrogens or chlorines and bromines together. So you have 8 hydrogens and 1 bromine, that is 9. Because for hydrogen, you add bromine, chlorine, iodine, whatever number you have. So that's minus 9 over 2, which equals 8 plus 2, 10, 10 plus 1, 11, 11 minus 9, 2, 2 over 2, which is only 1. So this molecule has only 1 double bond, or 1 ring system. Either you can have one double bond or one ring system for this. C8H8O is say 2 times 8, the number of carbons, 8, sorry, that's 8, not 6, plus 2, which is 18, minus number of hydrogens, 8. Oxygen doesn't count, so that's in the formula you don't consider oxygen. So it would give you that. That is 18. 18 minus 8 is 10. 18 minus 8 is 10. 10 over 2 is 5. So, for example, for this, what I would have is, if you have 5 degree of unsaturation, let's put one ring system, for example. Let's put it as a benzene, that is 4 unsaturation already. Since the number of carbon is 8, I can have, this is 6, 7, 8, 1 double bond. Total degree of unsaturation, ring plus double bond, is 5, meaning that one ring, 2, 3, 4, 5, C5, C8, and you have oxygen. I can put oxygen with hydrogen here, like that. So this formula is C8H8O. So that's one possibility, meaning that I put 4 degree of unsaturation, 4 alkene groups, or 4 double bonds, 4 pi bonds, and one ring. That is 4 plus 1, which is 5. It can be all just alkenes. So, for example, if I do 5 degree of unsaturation, it can be with 8 carbons. Let's say 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8. And I have 5 degree of unsaturation. So 5 degree of unsaturation can be 1, 2, 3. But this would not be possible, because if I have 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8, what I need to have is, for example, I need to have another pi bond, which would be, for example, 2 pi bonds here, and another pi bond. This is just an example. If you have a triple bond, which should be straight line, 1, 2, 3, 4, 5, 6, 7, 8. So that could be 5 degree of unsaturation, but that could be like this, OH. So the formula would be correct for C8H8O. Whether that compound exists or not is just something we have to experimentally see. But in any case, this is ring plus double bond, which is 5 of them. So as a review, ring plus double bond can be calculated by 2 times the number of carbons plus 2 plus, if you have any nitrogen in the molecule, number of nitrogen, minus number of hydrogens and halogens. Oxygen doesn't matter, divided by 2 would give you the right number of degree of unsaturation. So the calculation for this molecular formula, these are molecular formula, and this is degree of unsaturation, degree of unsaturation. Degree of unsaturation can be rings plus double bond. So this is just easy introduction to alkenes. How many alkenes can you have in a formula? That can be calculated by that formula. Okay, we'll continue. Okay, in the same line what we have just done, there is this question where it asks you to list all possible structures. That means it is an unsaturated system. Obviously, it is C10H14. So the first thing you have to do is, first we're going to have to calculate the ring plus double bond for this. So the ring plus double bond, 2 times 10 plus 2 is in the formula, plus 14 hydrogens over 2 will give us the number of rings or double bonds together. This is 20 plus 2, 22, 22 minus 14, 8 over 2 is 4. So this is a highly unsaturated compound. That means it has at least 4 alkene groups, meaning 4 double bonds, or it could have 1 ring system and 3 double bonds. Usually I would start with, for example, one example to list all the possible structure. If I have 1 ring system, usually in the Bayesian ring system there are already all of this are 3 double bonds plus 1 ring system. This is already 4. So my formula is almost ready now for the structure, but I have to give 10 carbons. This is already 6 carbons is accounted. So 7, 8, 9, 10. This is for ring plus double bond, which is and it has carbon, which is 10. If you count, this is C10H14. How do I know? You have 1, 2, 3, 4, 5 carbon, 5 hydrogens, 7 hydrogen, 9 hydrogen, 11 hydrogen, 11 here, 14 hydrogen, because there are 3 on this C10H14. But this can be also written as, for example, if I have taken out one of the double bonds out of this, and if I have this, and if I just put this one of the double bond outside and put it here, this is also the same thing, because this would be also 3 double bonds and 1 ring system would give you still 4 degree of unsaturation. And the number of carbons is 6, 7, 8, 9, 10. This formula is still C10H14. And I can also do now just have only 1 double bond inside the ring system and put this 6, 7, 8, 9, 10. So this is also C. So you can exercise this by writing every possible. You can make all alkenes possibly, meaning that 4 unsaturation, 4 alkene groups, and straight chain. So that can be also done. For example, let me just try this. If I have 10 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So can I accommodate 4 degrees of unsaturation? 1 here, 2 here, 3 here, 4 here. So if I have 4 unsaturated system, double bonds, this is the formula C10H14. Let me count the number of hydrogens. 3 hydrogens here, 4, 5, 6, 7, 8, 9, 10, 11, plus 3, 14. So this is also correct. So the question was to list all possible structures that satisfy a C10H14 and with 4 degree of unsaturation. 4 degree of unsaturation. So we now, as a review, we now need to know how to calculate ring plus double bond if a molecular formula is given, and to write all possible structures. Ring always counts as a 1 unsaturation, and of course counts as a degree of unsaturation. So for C10H14, these are all possible structures with 4 degree of unsaturation. So with this, this is just a nice couple of practice problems for you to solve. Otherwise, it could be very easy for you to practice or to understand this. So now I'll continue to the next problem. Okay, the next question here you see on the board is how to identify a Z or E between these two molecules. So the question is, which one is E, which one is Z? These are two stereoisomers. These are marketed, for example, as a fertility drug, Clomid. Clomid is a mixture of these two stereoisomers. One is inclomiphene and the other is eclomiphene, and they are sold as Clomid, as a mixture of stereoisomers. So Z and E mixture, or Z and E are stereoisomers. Something you need to know is they are stereoisomers. The relationship between E and Z is a stereoisomer. Now we are asked to identify each molecule as Z or E. So the Z and E designation is important distinction to know from cis and trans. So cis and trans also can be used, but under a specific condition. Z and E are a more universal way of identifying the stereoisomers. Cis and trans applies when you have an alkene and you have only two kind of groups. For example, here if you have a phenyl and you have a phenyl and hydrogen and hydrogen. So the only group between on this whole molecule is a phenyl, and the hydrogen are the ones indicated here. So when the two are in the same direction, this is a cis, and when the two are in opposite of the alkene, for example, if it is phenyl like this and hydrogens like this, this is trans. So that's easy when you have two kind of groups on across the double bond. For example, you have one type here and another is hydrogen. So when you have two types and the two types are in the same side, the phenyl in the same side, the phenyl in the opposite side, you can tell cis and trans. But when it comes to this molecule, and the question is to identify it as Z or E, it has a reason. Because you have at least 3 different groups on the alkene. You have the chloride, the phenyl 2, and this phenyl, substituted phenyl, is different groups than the rest. So at least you have 3 different groups on this. If you have 4 different groups, obviously you have to do Z or E assignment. Here also the same thing. You have one group, which is the phenyl, 2 groups, and this phenyl, substituted phenyl, is different. So you have 3 different groups on Clomid in stereoisomers. These are stereoisomers. This is the inclomiphene and zuclomiphene. Clomid is 30% of the zuclomiphene and 70% of the inclomiphene. So to identify as Z or E is the most proper, not a cis and trans. Here you have only two groups across the double bond, meaning that these groups are one group, which is a phenyl group, and hydrogens. So that you can name it as cis and trans. When you have groups that are 3 or 4 different ones, you should identify them as Z or E. Let's identify this now. So you should always take the carbon and see what substituents are in this, which one would be high priority. So you have phenyl, but this phenyl has oxygen on it. So the priority would be for this one, high priority for this one. Between Cl and carbon, the priority is chlorine. So it's just by how you assign R and S. So chlorine takes priority versus carbon. Here, this phenyl is a substituted phenyl which has oxygen. If you just look at here, this is hydrogen here, but this one is oxygen on this one. So these two priorities are in opposite direction across the double bond. So this is called an E isomer because the two priorities, this is priority 1, this is priority 1. They are opposite to the double bond. Zuclomiphene, when it comes to zuclomiphene, you have a priority assignment between chlorine and phenyl. This is the priority 1. And between this phenyl and that phenyl, substituted phenyl, which has this is hydrogen, but this one has oxygen on it. So the priority would be for this. So the two priority groups are on the same side. Therefore, this is as Z. So this is the E. From the name itself, it's indicating that inclomiphene is the E. Zuclomiphene is Z here. So Clomid is sold as a fertility drug as a mixture of E and Z, where you have about 30% is Z and the rest is as E. So E and Z assignments are the same, close to the same as cis and trans, but cis and trans only works when you have only two different groups. But once you have groups that are more than two different groups, or like 3 or 4, you should use an E and Z assignment, not cis and trans. Cis and trans can be used for simpler groups where you have two different groups. Here I have a phenyl group and hydrogen. Two groups, cis and trans is possible. So now you should really know the distinction when to use E and Z, even though Z means as equivalent to cis and E means equivalent to trans. So that's how the distinction works. So E and Z are the most universal way of assigning alkene stereochemistry. So the E and Z are stereoisomers. Stereoisomers. Okay, so we'll continue more. Okay, let's see this problem here. And the problem set in asking about IUPAC naming of these alkenes. These are different alkenes as you see from A to E. Let's start by naming this. So you have to always find the longest chain that included the alkene itself, because that is the main functional group here in this compound. So in this case, it is 1, 2 position, 3, 4, so there are 5. If I redraw this looks like CH3, this is hydrogen, CH3 there, CH2, CH, and 2 metal groups. So that's how that looks like. So in the naming of this, it is a 1, 2, 3, 4, 5, 6. It is a hexene compound. So that's for sure. So what we're going to name this as is a 2 position is alkene, and at 2 position, at 3 position I have a metal, 4, 5. So this is a 3, 5. This is a 3, 5. Dimetal hexene. So in the 2 position is the hexene, so I will write 2 hexene, ENE, so don't forget. So this is 3, 5 dimetal, 2 position is the hexene. So if you really further want to give a full IUPAC name, what is the stereoisomerism for this alkene? So if you just look at between this and this, the priority is this metal group. And if you look at between this metal group and that group, this is the priority group. So the 2 priorities are in opposite direction. So this will be a 2E position. So the 2E designation shows us this is an E isomer, or usually what we call the trans isomer. Okay, let's move on to this one. This is a cyclopentene compound. Because it is an alkene, it is a cyclopentene. But in the substitution, you have sec-butyl, 1, 2, 3, 4. This is a sec-butyl group at 1 position. 2 position, you have a metal. So what we're going to say about this is a 1 sec-butyl, that would be a 1 sec-butyl, 1 secondary butyl, 2 position metal, cyclopentene compound. Still, we can also make the assignment for this, for example, whether it is an E or Z. From what I see here, the priority between this and this is a priority, this side. The priority between this and this is a priority. So this is an E because this is CH, but here it's a CH2. So this is actually a 1E position. So this is 1E. It's an E, 1 sec-butyl, 2 metal cyclopentene. Let's move on to this one. If you just look at this, the longest chain that included the alkene should be included. But importantly now, you should remember the priority between an alcohol and an alkene. An alcohol takes a precedent. Remember now, alcohol becomes top, then the alkene. Therefore, we should always include where the alcohol is included first, that chain, and also the alkene. So if you just count this chain, 1, 2, 3 position is the alcohol, 4, 5, 5, 6, 7. So this is an heptene compound, heptenol compound. The alcohol is the ending, the functional group we should write as 4. So that is a heptenol compound. So here if we just see 1, 2, 3, 4, 5, 6. That's not the one. If we just look at 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7. This is a heptanol compound. 1, 2, 3, 4, 5, 6, 7. So at 3 position I have the alcohol. At 4 position I have the isopropyl, and that's how. So how to say this? 4 isopropyl, right? So 4 isopropyl, and at 3 position I have that, but this is a heptanol. So enol, the in is 1, 2, 3, 4, hept 4 in, where the double bond is, hept 4 in, 3 ol. This is how you name it. 4 isopropyl, 1, 2, 3, 4. This is isopropyl chain. Hept, because 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7. That's hept. And the in is at 4 position. 1, 2, 3, 4. The alkene is at 4 position. The alcohol is at 3. So the alcohol takes a priority, so the compound is named at the final point. You should have the alcohol group. So that's 4 isopropyl, hept 4 in all. 1, 2, 3, 4, 5, 6, 7. That's correct. Let's see this one. If you just look at here, the alcohol takes the precedent again. So that would be the 1 position. So the alkene is at 2 position. 3, 4, 5. At 5 position I have isobutyl. So this is a 5 isobutyl, isobutyl. It is a cyclohexanol. So at 1 position I have that. So at 2 position, hex, in is at 2 in, 1 ol. So 5 isobutyl, cyclohex, 2 in, 2 position is this, and 5 isobutyl, cyclohex, 2 in, 1 ol. Okay. This is not isopropyl. Okay. Let's see in this one. We can still add here E or V. For example, if I want to add here, this would be the priority group for this side, and here it would be the priority. So it is an E position. So it is a 4E. 4 isopropyl hept, 4 in, 3 ol. And if we were to do this, so if you count here, 1, 2, 3, 4, 5, 6, 7, 8. This is octenol. This is an octene, obviously. So at 2 position I have metal, 2 position metal, 2, 3, 4, 5 position metal. So the way I would write it is 5 ethyl, 5 ethyl, 5 ethyl, 2 metal, and so this is 5 ethyl, 2 metal. At 2 position I have the in, 2 octene. is the name, 2-octene. 2-octene. 2-methyl 5-ethyl 2-octene. So then let's see assignment between these two. Since they are the same group on the same side, there is no E and Z for this. No E or Z isomerism for this, because these two are the same. Okay? So this is basically how you name it. The most important part is here, as you name in, which is the alkene, and the alcohol gets a precedence. So the final naming or the final functional group, the compound is referred as an alcohol. So well, we'll continue more as we exercise more of the naming. These are the IUPAC naming for these compounds. Okay, our next question is to draw structures for the names that are shown here. So I have compounds that are given their names, IUPAC name, from A to F, and our task is to draw the corresponding structure. So the first one, it says 3E, 4-ethyl, 3-heptene. So it's an heptene compound, which is 7 carbon chain. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. As you see here, at 3 position, I have the alkene group, and it is an E. So 1, 2, 3 carbon. This is an E alkene because this is a priority group. That's the priority group in opposite direction. Hydrogens are here, so that is a 3E. At 4th position, I have ethyl. So 1, 2, 3. A 4th position, an ethyl group is this. So that is the structure for A. That is 3E, 4-ethyl, 3-heptene. Now B says cis, that is a cis or Z, 4-octene. Octene is 8 carbon. So I'm going to draw an 8 carbon chain. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is 8 carbon. At 4th position, it is a cis-octene. So now the way I have drawn it will not give me a cis compound, because at 4th position it is 1, 2, 3, 4. This is a trans. So that's not how it should be drawn. This is the trans form, but to draw the cis, I have this, and this down. 1, 2, 3, 4, 5, 6, 7, 8. So this is cis, this is trans. So that alkene is a cis. So the right answer is the cis one, which is this. For C, it asks me to draw 3,3 dimethyl cyclopentene. It's very easy. At 3,3 position, there are 2 methyl groups, and it's a cyclopentene. First, I have to draw cyclopentane, and I make it cyclopentene like that. And at 3,3 position, I have dimethyl. So if I count this as 1, 2, 3, I have this. That is the 3,3 dimethyl cyclopentene. D, I have 4 vinyl cyclopentene. Vinyl, remember, this is an alkene group that's only 2 carbon as a substituent. So for D, a 4 vinyl is a 2-carbon substituent as a substituent for vinyl cyclopentene. That is cyclopentene again, 1, 2, 3, 4. So a 2-carbon alkene like that is a vinyl group. So that is a vinyl group. So this is vinyl. If somebody told you a 4-allylic one, just as a side track, and just want to show you the differences are, this is allyl. That is an allyl group, one more carbon as a substituent. 1, 2, 3 carbon, here 2 carbon. That's an allele. So for the question D, this is a vinyl one. Number E, it tells me that 2Z, 3-isopropyl, 2-heptene. If you are asked to draw 2Z, 3-isopropyl, 2-heptene, first you have to draw the heptene unit, which is a 7-carbon. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And at 2 position, I have a Z configuration. So at 1, 2, so to draw Z, the best way to do it is to do it like this. So the alkene would have a Z configuration. 1, 2, 3, 4, 5, 6, 7. It doesn't matter whichever way, but this alkene is a Z. At 2 positions, this is a Z configuration. At 3 position, I have isopropyl. 1, 2, 3, 3 position isopropyl. So that is the structure for 2Z, 3-isopropyl, 2-heptene. F, the last one. So you should be practicing a lot of this, and you become more perfect, because exercise is the best thing to do in this kind of problems. A 1-isopropyl, 4-propyl, cyclohexene. Cyclohexene is a 6-carbon ring system. I have this, and cyclohexene, obviously an alkene, but at 1 position I have isopropyl. Okay, isopropyl can be here if this is 1, 2, 3. At 4 position I have propyl. Propyl is 3 carbon. 1, 2, 3 carbon. So that is the structure for F. 1-isopropyl, 4-propyl, cyclohexene. So these are the kind of problems you would be encountering to transfer names into structures or structures to names. Okay? So we'll continue more on the same kind of problem.